Hello, so this is the Water as an Environment lecture. I wanted to spend some time thinking about how water is fundamentally different from like a terrestrial environment. So we can start with a really silly question. What is the difference between water and air? So think about that, think about what it means to be in an aquatic environment versus a terrestrial environment, and what are the challenges that an organism has to overcome. Now, what we can see is that there's basically different characteristics that organisms have that make them, good in one place versus another, right? Penguins, really good in the water, really terrible on land, even worse in the air, right? Whereas like a sparrow, um, or whatever this bird is. I'm not totally sure what it is. It's really good in the air. It's okay on land, right? It doesn't do too bad, but it's really terrible in the water. So when we think about the traits organisms have, due to the fundamental differences of water and air, they're going to be either good or bad in one. It's kind of like a trade-off, right? But there's four main differences that we see between a terrestrial environment and a aquatic environment. So that's gas availability, so how much oxygen is basically available. Thermal stability, density and viscosity, and then salt balance. So we'll kind of spend some time thinking about those four things. So gas availability. So what we know is that gas just moves really, really quickly in the air, right? In water, then, it takes forever for gas to diffuse, to go through, right? There's just basically more matter in the way, and it's harder for oxygen. CO2 is 10,000 times slower, right? So it's basically how big the gas is determines how fast it can go through the water. And then let's jump over here for a second. Oxygen is just much more available in air, right? It's 21% per liter of air, it's 0.21 liters of oxygen essentially. Okay, so air pretty much around the globe is 21% oxygen. There's real localized areas where there might be less oxygen, but it's pretty much the same. Now, water then is about 1% oxygen. So per liter of water, only about, we're not talking about, the oxygen in the H2O part, but if we're thinking about, free oxygen, O2, diatomic oxygen, in water, it's only about 1% of it. And what we see then is that there is, in non-photosynthetic water, so water that doesn't have photosynthesis actively going on in it, that's where we find essentially real low oxygen levels. Because there's bacteria and other things in water, they're continuously basically using up that oxygen. Oxygen is a chemical that is very reactive, and this is why we don't really find it on planets without life. And, really to find oxygen, there's a reason Earth is the only planet in our solar system that has a lot of oxygen, and because pretty much the only place we see it is photosynthesis actively creating oxygen. So in water that's really deep where there's no light, don't find oxygen. Water that's really turbid. Turbid means like cloudy, right? You can't see through it. So down in this. Oops, I'm sorry. That part of the river here is where we find, there would be less oxygen than the clear water that's in here. Water that's shaded or waterlogged sediments. Basically, wherever you don't find light, you can't have photosynthesis, therefore you'd have very low oxygen levels, unless there's like a flow of fresh water bringing that oxygen into that non-lighted area. So the other thing I wanted to talk about was a boundary layer. So let's say, here we have a area of sediment, or any surface. It doesn't matter. This could be the surface of a gill. Let's say it's the surface of a gill. That maybe makes a little bit more sense, because what you would have here is as water is flowing over a gill, it's not just like it's yes, water would flow into the mouth of a fish and flow through the gill, and we think about that oxygen diffusing into the bloodstream of the fish. Like the water up here has a lot of oxygen, and then the oxygen makes its way into the gill. The thing is, that's really tricky because of this thing called a boundary layer. It's not just like all that water is replaced. As you get closer to the surface of the gill, and now this is what we're talking about, like sub-millimeter scales, like microscopic scales. As you get really, really close to that gill, what we see is the water starts moving slower, right? So because the water molecules that are in contact essentially with the surface of that gill, while they're not like stuck to that gill, there's a lot of friction between these red water molecules and the surface of the gill, such that this layer is essentially not moving. And then, the next layer up, the next, molecules up are essentially moving very, very slower, getting faster, and finally water flowing freely across that gill. So if this water, the redder water molecules here, are essentially not moving, what that means is the oxygen has to diffuse through. They can't just travel with the water, because then all the oxygen essentially would just stay up here and not get to the actual gill. So boundary layers at the microscopic scale make it harder for oxygen to move through places, and that's why we see this, at real microscales, the oxygen dynamics are really much more different than what you might expect. So what we see is there's plenty of organisms that breathe water, essentially, right? That extract oxygen from the water. Most fish is what we see. But there's plenty of aquatic organisms that use air. A lot of the aquatic insects have this little predaceous diving bug. Has like basically a little snorkel that they put up, and then they can diffuse the oxygen up here will diffuse into that snorkel into the body of the bug, right? And this is relatively common. You see these kind of snorkel things in lots of different species. Mosquitoes, larval mosquitoes will do that, and then there's all sorts of aquatic insects that will breathe air. On the fish side, though, we see there's a lot of fish have this thing called a physoclist gas bladder. Okay, so when you think about a fish, one of the things that they have in their body is this gas bladder here. Okay, and in it is a mix of gases. It can be carbon dioxide. That's mostly what it is. There's some oxygen in it. Now, in what we call a physoclist gas bladder, it's basically a closed system. Okay, and how they put gas in and out to, if they put gas into the gas bladder, the fish will, basically rise up, or they can take gas out of the gas bladder, and then the fish will go down. In a physoclist gas bladder, it's just done via these the gas gland, which is right here, right? And that is done just through capillaries and blood. Okay, but this fish with a physostome gas bladder, you basically can gulp air, and there's this tiny little pneumatic duct here that has gas. Basically, the fish can go up to the surface, gulp air, swallow it into its stomach, and then it goes into the gas bladder. And that's cool because this is what you would see in a like a koi on a koi pond. And oftentimes you'll see them on a hot day coming up to the top of the koi pond and like gulping at the top of the water. And what they're actually doing is they're swallowing air, putting it into their gas bladder, and then there's all these little capillaries in here that can absorb oxygen. So there's plenty of ways for organisms to basically get around this idea of get around the problem of low oxygen in water. So when we think about oxygen, though, one of the key things is how oxygen is basically mediated by temperature. Okay, so if we got temperature here on the x-axis from cold, to warm water. Now remember, 35 is pretty warm, 90 some degrees or whatever. But what we see is oxygen goes down. Okay, so you have less oxygen able to essentially exist in really warm water. Now, why is that? So essentially, with warm water, the molecules are further apart. So look at this thing here, right? So if we think about, an oxygen molecule here, and let's say this is like a cup of water, okay? Water molecules are about the same size as, two oxygens put together. But when you think about warm water, the water molecules are further apart. So think about this oxygen escaping. Okay, there's essentially more room for it to slide between these molecules because they're literally further apart. Whereas in cold water, you got an oxygen molecule here at the bottom of the cup. It's really hard for it to get out here, right? There's less space in between these water molecules, and the oxygen can't get out. So this is why we think of heat pollution as like you can have thermal pollution, right? So if water essentially gets too hot, oxygen leaves the system, and this is why you have in late summer when lakes get really hot, you can have fish kills. So these fish here are dying essentially because there's no oxygen in the water, and they are all essentially running out of oxygen and dying. The other common time when you have fish kills is during late winter, at the end of the winter when there's still ice cover and maybe a lot of snow on top of the ice because light can't penetrate through the snow and ice into the water. But that's for a different reason, right? That's because basically all of the bacteria use up the oxygen over the winter, even though it's cold. So what we see now is, warm water has low oxygen, cold water has high oxygen. So organisms that are using water then to extract their oxygen oftentimes has this thing called countercurrent blood flow within their gills. Look at this little diagram here. If you have blood flowing this way and water flowing this way, let's say you start with blood that has 10% oxygen in it or something, right? You get a net, diffusion from the 100 to here, flowing into the blood. But once you reach 50-50, essentially you're going to have no more net flow of oxygen into the blood. So the blood can only get 50% saturated with oxygen. However, if you have blood flowing this way and water flowing this way, let's start about where the water just comes in, right? So it has really high oxygen, and there's a small gradient here from 80 to 75%, but then you have a gradient all the way across wherever you're looking at. So when that blood flow comes in with real low oxygen, even though the water doesn't have that much oxygen left, it has a small gradient such that oxygen will continuously flow into the blood. And then you can get blood that has basically 100% oxygen saturation at the end of the gill. This also happens with heat. If you look at duck legs, if you were to draw. I'm terrible at drawing, but you know, you have a duck here. Ooh, super good duck, right? With their little feet in the water, their webbed feet, right? What you have is you'll have a blood vessel going in and a blood vessel coming back into the leg. And you might wonder, you know, like when ducks are swimming on really cold water, how come their feet don't freeze? Or how come their body doesn't freeze if their legs are in the water that whole time? And the answer is their feet, yes, do get cold, but the really warm blood coming into the leg heats up that blood coming into the body, such that the body never really it loses some heat. You know, there is some heat lost off of the feet, but most of the heat from the core of the duck is preserved due to this countercurrent exchange that's happening just like over here. So one other way that we see organisms absorbing or holding on to the oxygen that they do have is with really slow metabolism. Okay, so this diver we see here, this free diver, what's actually happening here is I'm not sure if he has a weight belt or not. He might, but basically he's deep enough such that his lungs have basically collapsed enough, and so he's no longer buoyant. And when I think he might have a weight belt. Doesn't matter. But he's not actively swimming down, and all he's doing is jumping off and letting basically gravity bring him down, and then he doesn't have to use oxygen as he's swimming down. This tripod fish here has, I don't know if you can see it very well, but there's a big long spine coming off of the tail, and their two pectoral fins. And what it can do, it can just set up on the bottom of the ocean. So this is at the bottom of the ocean. This is actually saving oxygen and energy. And it's basically waiting for prey to come along. And finally, when prey come along, then it'll get up and swim after something. But it won't basically use any energy just by sitting and staying there. So what we see is, you know, a lot of organisms, the fact that they're cold-blooded, the fact that they have really slow metabolisms means that they don't use that much oxygen. Some organisms have really high hemoglobin then. These are bloodworms found in the bottom of a lake. So if you look at the sediments of a deep lake, oftentimes you'll find these bloodworms. They're, you know, relatively big, but they're red because they have that hemoglobin. It's differently shaped. It's not the same hemoglobin that like you and I would have, but it serves the same function, and that's why they are such that deep red color. All right, so let's move to the thermal stability of water then. Water keeps its temperature, but it's also hard to heat up. Okay, so and that has to do with its specific heat. So the definition of specific heat is the amount of energy required to raise the temperature of 1 gram of substance 1 degree Celsius. Okay, so basically, how much energy does it take to increase temperature? Now, if you look at something like copper, a metal, it's really low. For 1 gram of copper, you only need 0.385 joules to increase it 1 degree Celsius. Okay? Air requires 1 joule of energy, but water requires 4, over 4. So what does that mean? What it means is it's really hard to heat up water. Okay, and water has the higher specific heat than almost anything. There's a couple of substances that would have higher specific heat, but they're, you know, really not really found in nature. And what's happening here is, okay, you got an oxygen with 2 hydrogens. Now, remember that there's hydrogen bonds between here. The electrons spend more time over here, so there's a net negative charge there and a net positive charge up on the hydrogens. So when what comes up next to it is, so for some reason my drawing thing makes those every once in a while, and I can't fix that. I don't know the problem, right? So you've got a net negative here next to the oxygen and a net positive. So what there is there's this hydrogen bond. It's a real temporary bond, but that happens between the positive hydrogen and the negative oxygen. You can think about it as like they kind of just give each other a high five for a second. But it lasts only a trillionth of a second, really. But when you have all of these hydrogen bonds happening between the trillions of molecules of water in, wherever water you're talking about, all those little bonds do lots of things, like cohesion, but what we're talking about here is with heat. Essentially, it takes a long time, it takes a lot of energy to first break all of those hydrogen bonds and then get the water moving. You could make it an analogy of, think about a ball pit, okay? And remember, heat is just kinetic energy. So how much energy does it take to stir up those balls in the ball pit and get them moving? Now, if you have just normal balls, well, you can imagine, if you have a bucket of balls, it's just easy to move them around. But imagine that all of those balls then have little pieces of Velcro on them that stick to the other balls. It would be a lot harder to get those balls moving in that bucket. You'd first have to break those Velcro bonds before you can get those balls moving. So it's a lot harder to heat up those balls. It's a lot harder to heat up water because of these hydrogen bonds. So water holds its temperature over time. This is what moderates our body temperature, right? So one of the reasons when you're doing exercise you don't overheat is because we're mostly water. But it also moderates like global temperatures too. So if you look at, this is a temperature map, and what we can see is wherever we're close to the coasts, it's a lot warmer, right? So look at, the middle of Canada versus over here on the edge by, Alaska and British Columbia, right? It's a lot warmer. The bluer temperatures are colder. It's a lot warmer the closer you are to the water because that water is holding heat. And if you look at Ireland, right? Ireland is right here. And you see it's kind of like that orangey, yellowy color. That's at 53 degrees north, okay? So Ireland, is up at north of, middle Canada, right? But if you look at where in the U.S., in the continental U.S., can you find that yellow-orangey color, it's pretty much like in Oklahoma, right? So actually on the southern coast of Ireland, you can find palm trees growing. And it's really weird, but what they have is, because they have this flow of warm water coming up from the Gulf Stream, it keeps Ireland relatively warm. Now, it's by no means a tropical climate, but it does keep it warmer than you would expect based on its latitude and comparing it to like the middle of Canada at the same latitude. Okay, now I want to spend some time thinking about the density of water. This is really important because the density of water and figuring out why water has the density that it does is really, really key to understanding a whole lot of other things going on in this class, specifically the vertical environment lecture that we'll get to. But so I really want you to think and be sure to figure it out. We'll also go over this probably in class at times. All right, so first off, water is really dense, much more dense than air, right? 784 times denser than air. And right, like this person doing a belly flop is experiencing that very clearly. Because of that density, then, an organism doesn't need as much supporting tissue. Okay, so if you look, this is something called sea lettuce here, and it's this really frilly stuff that you could just basically, if you bring it out of the water and put it on land, it just heaps into a big pile, right, and wouldn't do well. Same with this, like really transparent, really jellyfish here. It doesn't need the supporting tissue because it holds itself up so well. Okay, now what I do want to spend some time thinking about is the physics of water density. Okay, and in specifically with temperature. Okay, so how we know that water gets really floaty, shall we say, when it gets to be ice, right? So this graph is a little confusing to think about, right? So what we have here is less dense on the bottom and then more dense here on the top, okay? So what we can see is ice is much less dense than water. Okay, we all know that. But actually, it's interesting. As ice gets colder, right, you get an increase in density. Now, this increase in density isn't that much, but it does happen, okay? The interesting part is what happens from 0 degrees up to, essentially boiling, okay? And what we see is the density of water. Maybe let's start with hot water, okay? Over here at hot water, the molecules are really moving around a lot. So the fact that they're moving around and bouncing into each other keeps them far apart. So it makes them less dense, right? As they cool down, they start to get less and less dense. Sorry, more and more dense, because they're not bouncing off each other as much. And finally we get a peak at 3.9 degrees. Let's just call it 4 degrees Celsius. Okay? Now, so we get the most dense water at 4 degrees Celsius. Okay? But then we see this decrease in density from 4 to 0 degrees Celsius. Now that's a little bit confusing because we always think of as colder stuff as being more dense, right? This is why hot air balloons work. Hot air balloons work because the hot air in their balloons are less dense and allows them to be buoyant and float up. So what is actually happening though? So let's go from this hot water to cold water to ice, okay? So at warm water, right, we've got the water molecules pretty far apart from each other. As we cool down, those water molecules get closer to each other. But then as they freeze, then they get really, really far apart from each other because those hydrogen bonds, that's what this little green dotted line here is, becomes essentially semi-permanent, almost permanent. Now they can still break and reform, but you get a crystalline lattice of water molecules, okay? And so when we see that, that increase in density and then that decrease, and then this here is at 4 degrees Celsius, right? What's happening here in this portion of that graph is that these water molecules are starting to form this crystalline lattice, right? Those hydrogen bonds are starting to last longer and longer. So it's, these hydrogen bonds in here are starting to last longer and longer, and they're starting to push the water molecules apart such that it gets less and less dense. Now this is important then because it allows essentially ice to float. And if we were to have ice that would sink in the oceans, there would only be a couple meters of non-frozen water essentially if ice were to sink. But it doesn't, so we don't have to worry about that. So go back here, look at this graph, draw it out, explain, why we see all of these, at 0 degrees Celsius, and then this increase in density to peak at 4 degrees Celsius. Draw this several times, figure out what's going on, because it's really important for the rest of this course. So when we look at the density of water, pretty much any organism is going to be denser than their water than the water, right? Like fish have bones, which makes them, if they don't have this gas bladder, they're just going to sink. Okay. Even just like muscle tissue, if you put a piece of steak in water, it will sink, right? So organisms have to find ways in which to either, depending on what they want to do, if they want to float, well, they better have gas bladders and oil droplets. This is Utricularia. It's a plant that each one of these little things has a little bubble of gas that keeps it floating up top. This is a diatom that has oil droplets that allow it to float because its silica cell wall is really dense, actually. So they have these oil droplets inside them. It's essentially like fat that allows them to float up towards the top of the water column. Now fish then want to do something a little different. They don't want to be just totally floaty, right? They want to be able to be neutrally buoyant such that they can swim through the water and change elevation basically in the water so that they can control the amount of gas in their gas bladders just like a submarine would. So most organisms have some ability to, or some adaptation to deal with buoyancy depending on what they essentially like want to do. Okay, this next section is a little bit confusing and it kind of takes a long time to explain, but it'll be worthwhile here. So I would pause the video if you don't have enough time to like listen to this whole bit, but please spend some time to listen to this whole thing, the whole story here. So start out this discussion thinking about, if you want to swim fast, what do you do? And what I mean by that is, how do you position your body? Okay, what you want to do as a human, a normal-sized human, is essentially make yourself as streamlined as possible. Okay, so the way we experience water is that we want to make ourselves streamlined. So, but at different sizes, we need to think about different forces. Okay, so there's two forces in play, which is essentially like inertia and viscosity. So viscosity is the magnitude of internal friction, right? So take a glass of water and a cup of honey and pour them out. There's more internal friction in the honey. It has higher viscosity, such that the honey particles are essentially sticking to each other, and it takes longer to pour out a cup of honey than it does to pour out a cup of water. Now, I said there's also inertia. Inertia is the resistance to change in motion, right? So when you're swimming, this person here wants to basically limit their frontal surface area, right? So they make a diving into the water, right? So think about these four people here. Who is experiencing the worst, the most force? And essentially, this guy in the back here is just fine. This guy's just fine. Whereas these two people up in the front, particularly this guy, you can see it on his face, right? He's experiencing the brunt of that force, right? Same with this person, right? All of that water is hitting the face of this person. So to swim faster, what we want to do is not have that frontal surface area. Because think about, how much water is in front of you. When you're standing up in chest-deep water, you've essentially got water from, your chest all the way down to your feet, that as you walk through that water, you need to move essentially this heavy water that has a lot of inertia out of the way. Or you can position yourself such that you only really got an area maybe 1.5 feet by 1 foot that you need to move, of heavy water that you need to move out of the way. Okay, so this is why submarines are shaped the way they are, long and skinny, right? Essentially, if you want to make a bigger submarine, you just make it longer. You don't make it wider, right? It needs to be some amount of wide, right? But you don't make these really tubby circular submarines because there's so much frontal surface area, right? So if you just make this longer, if you were to just extend this submarine longer, right, you would not be pushing any more water out of the way. It would just be there'd be a little bit more drag, but at these size scales, that drag really is unimportant. Okay, so at large scales, inertia is the most important thing. The inertia of that water in front of you. So how do organisms deal with this? Well, streamlining is really, really important. Surface area doesn't really matter in this case at large scales, but so we see, just like those submarines, fish grow longer, right? Like if you get a 4 or 5 pound northern pike, this might be a muskie, right? That looks like one, but they're not that much skinnier than this maybe 12 or 13 pound muskie here. The bigger fish are just pretty much longer. And what they do is so they have real that frontal surface area is really what they're most concerned about. So they're very streamlined and tubular, kind of like cigar shaped, right? Now, at small scale, though, small organisms live in a completely different world. And it's hard to understand this world because we don't experience water that way. So if you want to swim fast at small scales, what do you do? And the answer is not actually be streamlined. Okay? Now, at small scales, the inertia of the water in front of you, so let's say you're this bacteria here with these flagella that are beating, okay? How much water is in front of this bacteria? Very, very little water, and that this water essentially weighs nothing. So the water, you don't have to worry about pushing this water out in front of you because you don't really push any water out. It's very, very small. Also, your body mass when you're a bacteria is very small. So if a bacteria were to stop beating its flagella and just coast, it coasts 1/10 the diameter of a hydrogen atom. Okay, so think about how small that is. So inertia of your body itself, there doesn't have any, but the inertia of the water in front of you when you're super, super tiny, you don't have to worry about that either. Okay? What is important is viscosity. Okay? The attractive forces between water molecules and the organism essentially become really important. So at super small scales, water becomes sticky. Okay? It's like bacteria and really tiny organisms, plankton and zooplankton, are swimming through honey. That's how they experience water. Those hydrogen bonds between the water can actually hydrogen bond between themselves and the organism itself, and that stickiness we still feel that, but it's like that's still happening to us. But the relative importance of it is just really small. Like it's such a small force that we essentially don't experience it. So, when you swim, if you want to swim at small sizes, what you need to do is reduce the surface area. So we see these organisms. This is a basmina. It's essentially circular, spherical. Okay, because if you're really tiny and you want to swim through water, you want to reduce the amount of area in which you're touching that honey. Because the more honey you touch, the more it's going to slow you down. So be spherical. You don't want to be this long tube like a really big long submarine, because then there's so much area for that water to like stick to you. So if you want to swim at small size, be round. Okay, but now let's think about the opposite. What happens if you don't want to swim? So if you think about, say, like a lake, okay? Super good lake here, right? With the water column. Let's say, below this level, it's dark, okay? So if you're a phytoplankton, an algae that's living up here, you do not want to sink down here, right? You're going to die. You're going to not, once you get into that dark, once you sink down into that dark area, you can't ever, like go back up, right? Because you're not swimming, essentially. You're just a plankton that is just kind of like floating there. So what we see is algae essentially want to stay up towards the top where the most light is. So how do they do that? Well, first they have like floating mechanisms, but one of the things that they have is they increase their surface area with either like these little Asterianella diatoms here are really thinly shaped, and so they can stay up in the water column. Same with all these spines up here. What essentially they're doing is they're increasing their surface area, and they're putting out like little parachutes essentially in the water, so that when they're in that like honey water at that really small size, there's so much drag on those small organisms such that they never really sink. It's like all those spines hold them up in the water as like these almost like permanent parachutes that never let them sink, and then they can do their own thing and stay up in that water that is has light in it. All right, the last thing that I want to talk about is salt regulation, okay? Because that's very different, right? Like, how do humans regulate salt? Well, we either eat salt, or we pee out salt, or we sweat out salt, or, we drink water if we have too much salt. So it's like eating and drinking and excreting. There's other processes that go on in fish, okay? Now, we got to go back to like, introductory biology to think about osmosis, okay? So, and it's different in fresh and salt water. So let's talk about fresh water here. So what we see is hyperosmotic, right? The fish body, and let's just think about the blood, because all we really need to think about is how the blood is compared to the water. So the blood has a lot of salt in it compared to fresh water, right? Because fresh water essentially, doesn't have any salt in it. So if we just think about that, what's going to happen at the gills? Okay, when we think about osmosis, since this blood is hypertonic, water flows in at the gills. Okay, water flows into the gills. So from that sense, then, fish never really need to drink, right? When they swallow their food, drink a little bit of water. But a freshwater fish will never basically dehydrate, right? Because its cells are hypertonic, water is continuously flowing in. Those salts then are gained in their food, but essentially freshwater fish are continuously peeing. Because they have a continuous influx of water in their gills, they have a continuous outflux of water through their pee, right? And essentially what their pee, though, is their kidneys are working really, really hard to hold on to their salts. So, like, their pee is really clear, okay? Dilute urine. Also the gills are actively uptaking salt as much as they can, right? Because while this hypoosmotic, really dilute urine is really dilute, they still are losing some amount of salt. So their problem is to get enough salt in their food and from the water such that they don't like pee out all of their salt. That's what freshwater fish are dealing with. However, in saltwater fish, it's a different story. The outside of the water is extremely salty, right? So we got all sorts of salt out here, right? So a saltwater fish is losing water from their gills. Water is continuously flowing out. So what does this fish need to do? If water is continually going out of their gills, it needs to drink water continuously. But the thing is, what do we know about drinking salt water? So drinking salt water is bad for things that aren't adapted to it because there's so much salt in it, right? But that's the only way these fish can get water. So they'll drink the water and then essentially pee out, extrude. They'll pee out really salty urine and extrude salt from their gills. Their gills will be actively releasing salt. So if you look at the pee of a saltwater fish, it'll be very concentrated, but they don't want to do too much of it because they don't want to lose all their water. Like the more they pee, the more they lose water. So their kidneys are working really hard in a different way to make really, really salty urine. And they get some salt in food, but they don't really need that salt. So yeah, the problem for a saltwater fish is to get enough water in its body and without like totally oversalting its body. All right, that's it for this lecture. With that, I'll see you later.